give a brief introduction to Charles Friedman. He's a Joshua Macy Junior Professor of Medical Education and Chair of the Department of Learning Health Sciences at the University of Michigan School of Medicine. He has been doing research and education activity in health informatics and biomedical informatics over 4 decades. His recent passion is learning health systems, and the idea of the learning health system is discovery of putting in knowledge within the area of health with to create learning ecosystems. He has recently been awarded an honorary doctorate by University of Lausanne in Switzerland for his contribution to science of learning health system. Prior coming to the Michigan, Professor Friedman held executive positions at the Office of the National Coordinator for Health IT in the U.S. Department of Health and Human Services. Immediately prior to his work in government, Dr. Friedman was Associated Vice Chancellor of Biomedical Informatics and founding director of the Center for Biomedical Informatics at the University of Pittsburgh. So, when he is embarked on activity of biomedical informatics, everything is big. And I know of his work, of his books with Jeremy Wyatt a while back, which was recommended to all our students in health informatics master program. So I think they have also published a recent edition of it as well. Anyway, without further ado, I'll leave the floor to the Professor Friedman. Thank you.
Thank you, Abdul, so much. It's really a pleasure to be here and to have this chance to present to your faculty and students. You had to mention the 4 decades thing, didn't?
Sorry.
I guess I asked for that. Okay, I will share my slides here and get rid of the hanging floating meeting controls and go into slide mode. Okay, can you all see my slides?
Yes.
Okay, good, thank you. So I'm going to talk about 2 topics that are very near and dear to my heart, learning health systems and computable biomedical knowledge. And I will connect them through a concept called mass action. And before I begin, I do have to share this disclosure about a role I play in a nonprofit corporation promoting learning health systems. Now, doing that connection is going to require a bit of a journey. So this presentation will actually have 7 parts. And if we start running short of time, I might go lightly over some of them. But let's see how it goes. To tie everything together requires this many pieces. I hope they mesh together smoothly into a coherent presentation. And at the end, I'm going to introduce those of you who are not familiar with it to a global movement called MCBK, which stands for Mobilizing Computable Biomedical Knowledge, which is seeking collegiality and collaborative work to advance both of these concepts. So the first thing I want to say is that this talk is about knowledge and not data, or knowledge primarily and data only secondarily. So please put yourself into that frame of mind. We are so consumed with data these days. I think collectively we're kind of losing track of the higher purpose for which we collect and analyze data, and that is to create knowledge. And I think this talk is really about what you do with that knowledge once you've created it. Now, I'm going to offer a very informatical definition of knowledge that I'm sure would drive philosophers crazy, but I think this works for an informatics presentation. And this views knowledge as a result, and in particular, the result of an analytical and/or deliberative process, it could be both, that holds significance for an identified community. And this significance point is very, very important. I would argue that analysis by itself just makes data into what we might call proto-knowledge. And to become knowledge, it must be reviewed and endorsed by some identified community with some authority, to recognized authority to provide that endorsement. And you see the process here going from data through analysis to knowledge, and through to proto-knowledge, and through endorsement to knowledge. And you'll understand why I use the keystone icon in just a few minutes. So to bring this a little closer to the surface of the earth, let's look at some examples of biomedical knowledge that follow from viewing knowledge as a result. And I have these examples here arrayed from those which result from primarily analytical methods to primarily deliberative methods, although none are purely one or the other. So at the top of the continuum are predictive and explanatory models, followed by computable phenotypes, causal and propositional networks. Now we're getting into the middle with best practice guidelines, where, as we know, they result from both analytical and deliberative processes, decision trees, which are moving us closer to the deliberative end, and finally policies, which can be viewed as a form of knowledge, which anchor one end of the scale by coming primarily from deliberative processes. So this moves us on to point 2, learning health systems and mass action. So a simple way, a straightforward way to understand learning health systems is that they lead to improvement against health problems of interest by marrying discovery with implementation via cyclical processes. So here is a representation of a cyclical process that is commonly associated with learning health systems. There are many variants on this, but they all share the basic idea of cycles, discovery, implementation, back to discovery. And in this conceptualization of an improvement cycle, the beginning is with the formation of a learning community that shares a passion to solve some health problem with interest. The first step after the formation of the community is capturing practice as data. What is going on now, captured as data, and what is the outcome? How well is the system performing with regard to this health problem at present, against which you want to improve? Then comes the non-trivial task of assembling that data for analysis, cleaning it, and all the other things you want to do prior to analysis, and then doing some kind of analysis which converts those data to knowledge, usually relating what is done to what the outcomes are. And that internal knowledge sits there at 12 o'clock and is combined with external evidence, because it's very, very likely that any health problem important enough to generate interest and passion is going to have been studied elsewhere, and there will be reports of those studies in the literature. So at the top of the cycle, the community comes together to interpret these results, both the internally generated knowledge and the externally generated knowledge, and collectively decides what to do, and co-designs an intervention or interventions. Now we're on the implementation side of the cycle. Those are then implemented. Action is taken that changes the system and probably changes the result. And studying this new practice and these different levels of outcome provides the data for the blue phase, or the data to knowledge phase of the second iteration of the cycle. And around through successive iterations, particularly with regard to wicked or intransigent, previously intransigent problems, it is believed and is currently being demonstrated that significant improvement can occur. So the bottom line is that better health requires these complete cycles, marrying discovery to implementation. And I want to point out, not this, which is what all of us were trained to do, and which got me tenure and made me into a full professor. That is collecting some data, converting it to knowledge through analysis, publishing it into a journal, and then going back and collecting more data, analyzing it, and publishing that in a journal, and doing all this with the best of intentions and the belief that there's someone here just waiting for this article to appear and to do something with it. But as we know, that is not the case, and it is widely recognized that it's many, many years of latency, often as many as 17, between the discovery of new biomedical knowledge that can improve health and healthcare and its widespread implementation in practice. So what we don't want is another way of looking at it somewhat equivalently is a gap at the top. We, even if we intend to continue this cycle by moving from discovery on this side to implementation on this side, there's a gap, and the process often stalls here. Look at what joins the blue to the red, the K and the K. It's knowledge, and in what form this knowledge is represented can have a great deal to do with whether the discovery portion of the cycle leads smoothly into a scalable and sustainable implementation. So we can view knowledge, and here's where the keystone comes in, as the keystone holding the cycle together. Without some representation of knowledge, without a solid keystone at 12 o'clock in the cycle, that gap can be insurmountable. Now, what I'm going to suggest is that by putting this knowledge into computable form, it can close the gap in such a significant way that you can call what it enables a second knowledge revolution. Let's look back in history, hundreds of years, to the 15th century, and recognize that the first knowledge revolution, which was enabled by the invention of the printing press, enabled mass access to knowledge. Knowledge was limited to the clergy, the nobility, and the rich, who could afford handwritten manuscripts capturing what is known at the time. And the masses did not have any way, even if they could read, and many of them couldn't, to what is known in the world about the world. The printing press changed all that, created an incentive to learn to read, and we of course know what resulted. It's the modern world in many respects. So this was truly a knowledge revolution in the 15th century. Well, I believe that mass access doesn't cut it in the modern world. In the modern world, and particularly if we are going to improve health using learning health systems at scale, we have to go beyond mass access to mass action. And mass action has three features that I will introduce briefly here and will return to. Mass action requires or enables delivery of interventions, whatever they are, driven by knowledge at unlimited scale, even to the point that 5 million, the intervention could be delivered to 5 million recipients as quickly and easily as that could be delivered to 50. Since knowledge is changing very, very quickly, when knowledge changes, when knowledge related to health changes, the implementation can be large scale and instantaneous, because if the knowledge is computable, it's represented in software, and software obviously is much easier to modify than print on paper. And third, synergy among these knowledge elements that we are later going to call knowledge objects can generate interventions that are truly synergistic. The value of the combination of these objects, because they can interoperate, because they're computable, can have a value to improve health that exceeds the sum of their parts, which of course is the definition of synergy. So the connection here between learning health systems and computable knowledge is that it enables this second knowledge revolution that holds the potential to improve health at scale through mass action. Okay, I talked about computable biomedical knowledge. What did I mean by that? So let's begin by entertaining that in the modern world, through digital technology, there are now two complementary ways to represent knowledge. The first is the product of the first revolution. It's human readable knowledge in words, pictures, equations, symbols of all sorts that can be read. And it doesn't matter whether it's read on paper or read on a screen from a PDF, that is still human readable knowledge. The second way is computable knowledge, where the knowledge that is in the human readable document is represented in code. And I don't know if you can see this on your screen, but what's in the middle of this abstract representation of what we're going to call a knowledge object is sets of ones and zeros, which of course is the fundamental representation of code for use by a machine. So let's talk about how one can become the other. So let's start with a paper, very familiar, paper in this case from the New England Journal of Medicine, in human readable form. Somewhere nestled in this paper is the result. And the result of this study is a predictive model. And the essence of this predictive model is captured in table 2, which gives you the coefficients of what is, in this case, a logistic regression model. And down here, the author conveniently provides a guideline for how, if you actually want to compute a prediction, a lung cancer prediction from the relevant data about a patient, here's how you do it. And the author goes further as to offer an Excel spreadsheet in case you want to do this in Excel. And when I saw that, I didn't know whether to laugh or cry. More cry than laugh, I believe, when you think about all the problems of trying to disseminate knowledge like this in a quasi-computable form in an Excel spreadsheet. But moving on, the knowledge in that paper, the model, the result, can of course be made computable by representing it as code and packaging it into a knowledge object with, at its core, what we call the payload, that is a routine that takes in the characteristics of a person as specified in that table 2 and computes a risk score for that person. The outer layers of the knowledge object specify how to interact with it, which is also in code. And on the very outer layer, metadata about the object, what it does, where it came from, and other important information that will make it trusted That, of course, is not written in code. That is represented in human readable language. So if you believe, as I believe, that we are headed in a direction because of the potential of this second knowledge revolution, where we are going to increasingly complement human readable knowledge and put it in a library with a representation of that same knowledge in computable form and put that in a library. The news for scientists is that when you publish this paper and it goes in the library, you're not finished. To put it in computable form, not that you necessarily have to do this yourself, but someone has to, extract the model in a way that is encodable. In this particular paper, that was particularly easy, which is why I used it as an example, and we call that model extraction. And then some programming, and it doesn't have to be particularly sophisticated programming. The model is represented as executable code, and then the object, when instructions for how to access it and metadata are added, can go into what I call an expanded library. And my vision of a second knowledge revolution library of the future, just as it will have a collection of human readable knowledge, it will also have a collection of computable or machine executable knowledge. So that's the concept of computable biomedical knowledge. Okay, now, why is it essential for mass action? Well, this takes us to an interesting distinction between so-called discovery systems, such as I showed earlier, where the goal is simply to discover something and publish it in a journal. Not that that is simple. And learning systems, where the goal is to execute complete cycles, iterations over which can lead to significant improvement with knowledge at the keystone. Discovery systems require only mass access, human readable knowledge. It's sufficient to have human readable knowledge to engender mass access. And those of us who do science are very familiar with this process, whereby somebody collects some data, analyzes it, and publishes the result in the journal. And because of mass access, it's pretty easy for another study group to find that article, read it, and use it to inform their study, which they publish in a journal. And yet another study team finds that same article and uses it to inform their different study and publishes that in the journal, and on and on and on. And science progresses. And if you are only interested in discovery, mass access works pretty well. The good old printing press will, and its descendants will continue to serve us. However, human readable knowledge alone can't work for learning systems. We know that. It is an empirical fact that if you leave the knowledge in this form, you are going to engender the 17-year gap. You're certainly making it hard to jump this gap from discovery on this side to implementation on the other. For example, let's suppose what you have is this paper. How does it, even though it offers a potentially useful prediction model, enable change practice? It's hard. What do you do with this? Do you walk around on the street waving it, saying, hey, let's do this? And even if you do, there's really no instruction, no information about how to do it. You can build an Excel spreadsheet, but I think you can see that it's very, very difficult. So something else is needed to close this gap, and I think you know where I'm going with this argument, that learning health systems need computable biomedical knowledge to bridge this gap. And what you can see here represented is computable biomedical knowledge viewed as three knowledge objects. I think in the real world, we are thinking of thousands or maybe tens of thousands of knowledge objects in the future, computable knowledge objects in the future, forming a kind of computable knowledge ecosystem that can, through the potential of the second knowledge revolution, take health improvement to scale. So now let's revisit the points about mass action. Here we have a learning cycle being empowered by a collection of knowledge objects, and it meets the criterion for mass action using the power of digital technology to compute out of these knowledge objects. And I'll give you an example in a bit. Personalized recommendations, in that earlier case, a risk score, just as easily for 5 million people as it is done for 50. We're now viewing, back to our example, each knowledge object as a risk model for a particular type of cancer. Four are illustrated here. There could be many more objects included in this collection. When a new model is added, the implementation can be universal and instantaneous. Moreover, when a model is revised or supplanted by a better one, then its implementation can be universal and instantaneous. And third, a risk panel, which consists of multiple predictions for a clinician, perhaps, and an individual as well, is of far greater value in understanding the risks they take as their life progresses and how their lifestyle might be modified accordingly, then is a very separate and atomistic, separately delivered set of individual cancer risk scores. So look at this and see if you agree with me that this is what's coming. This is the modern world. This is not a talk about AI and machine learning, and I didn't show you an AI model, but these knowledge objects could be packaged AI models, could be packaged AI or machine learning generated algorithms that have the advantage that they come in computable form. No one has to convert, for example, a logistic model to a knowledge object or a best practice guideline, which, as we know from the literature, is often very challenging, but it can be done to convert into a computable form. But I guess what I'm arguing here is that when we look at this slide, we're looking at the future. We're looking at a future with mass action enabled by computable biomedical knowledge that can be used to continuously improve health through the cyclical methods of learning health systems. So just getting a little more informatical and geeky for a moment, let's just talk about what kind of mass action infrastructure you need to make all of this work. Well, there are four things you have to do. You have to represent knowledge in computable form. We talked about that, and package them as knowledge objects. We introduced that at least. My group as Michigan has actually published an ontology, an ontological representation of a knowledge object that I would recommend, if you're interested, that you might want to look at. You then have to establish a library that holds knowledge objects, makes them accessible, indexes them to make them findable. And when you put together the metadata with the knowledge objects, you can make them interoperable. And by having done all that, you can make them reusable. So these objects can conform to the FAIR principles. You then need an activator to actually generate an intervention. So these objects actually do something. And then you have to enable messages / advice to be delivered to whomever the recipients are and have the results received. So the first step is the representation of the knowledge in machine executable form. We've already kind of gone through that, but I would note that many different kinds of human readable knowledge, like guidelines and articles, as we've discussed, can be put into machine executable form and packaged as knowledge objects, as can local analytical results, perhaps already, if AI and ML methods were used, are represented in machine readable form. And then you package them with the knowledge payload at the middle, the interface, which contains the encoded instructions for interacting with the object, and then the metadata, which is human readable information to describe the object in all its splendor. And it turns out that we have published papers saying there are probably 13 kinds of metadata or categories of metadata that are needed to fully characterize a knowledge object. So you also need a digital library. And actually, a digital library, or a library that stores knowledge objects, is pretty much like the libraries you know, but just has a different kind of collections. And it maintains and protects knowledge objects. It will guarantee that the objects that is furnished to you are authentic and have not been altered, and it enables them to be shared and returned. And then an activator, which you probably can ordain already in terms of what it needs to do, how it works. And the activator needs to extract knowledge objects from the library. It needs to strip the payloads using, in order to do that, the information encoded in the second layer, the implementation instructions. It then knows what data are needed to enable the knowledge object to execute whatever it needs to execute, and imports that data. It puts a call out to wherever those data lie to obtain the data, and then it computes an intervention. Then the next step is connecting the results or the intervention to the world of EHRs and apps, which are increasingly accessible, which is increasingly easy to do. Not that it's easy, but it's increasingly easy through standards-based open portals and APIs. So the fourth is a mechanism for actually making the knowledge object or objects that are computable, usable and scalable, and make the mass action principle actually work. Now, it turns out we've spent about 6 years building an infrastructure that supports mass action in learning health systems. It's called the Knowledge Grid, and it's a product of our Knowledge Systems Lab, and it's being used in several places. There's an article in the Learning Health Systems Journal that describes how we do what we do using the Knowledge Grid with an example of an application that's actually in current use at the Cleveland Clinic. Now, the example I'm going to give you to bring this a little bit closer to real life is one in the domain of clinical pharmacogenomics, where if you go to a website for the CPIC in the US, which is the Clinical Pharmacogenetics Implementation Consortium, you will find a lot of tables which basically for a lot of different drugs where the science is known, basically how to administer or alter the recommended dosage of a particular drug, in this case, codeine, based on the patient's phenotype derived from their genotypic star alleles. And This is human readable knowledge. I can't imagine how this can be used as scale. This is first knowledge revolution knowledge, and it's certainly readable and it's certainly accessible, but how do you make it into mass action? Well, the first thing you do is you array this information in a form that a programmer can work with. So you make a table out of it, and then you ask your programmer to represent this table in executable code, and then you add the implementation guide and the interaction guide and the metadata, and voila, you have a complete knowledge object representing in machine executable form what is in this table. About 4 years ago, maybe 3 or 4 years ago, we completed a project where we made into machine executable form all of the recommendations of the CPIC which existed at the time. I'm sorry to report we haven't done all that much with it since then, in part because we couldn't find a partner to work with, but this work stands ready to move into the world. We've had more success in other domains, such as work we've done to put the U.S. Preventive Services Task Force recommendations into machine executable form, all of the grade A and B recommendations, and that's what's in use in Cleveland Clinic at the moment. So just to cap off the point here, the current state of CPIC's guidelines only allows mass access, because the guidelines are available in only human readable form in tables. And the future state enabling mass action, which we hope to do soon, will be to put them in fully computable forms, have them available through a trusted digital library available to anyone who wants to use them. They have been developed with support by the US government, so they have to be in the public domain. It'll also require activation services that use the objects in combination with individual patient data to generate advice, and then they must deliver advice through apps or EHRs. With these 4 steps complete, all the criteria for mass action will be satisfied. Finally, and I'll finish up here in just a couple of minutes, there are a lot of people around the world, and a growing number, who are interested in mobilizing fair and trusted computable knowledge to improve health and healthcare. This movement started in 2017 with an invitational meeting just to verify that we're not crazy in proposing this, and the group felt on balance that we were not crazy, a little ambitious maybe, but not crazy. And this was succeeded by 2 in-person meetings on the NIH campus, a meeting in the UK where the late John Fox, who became a major proponent of computable biomedical knowledge, spoke. He sadly passed away a couple of years ago. We then moved with the pandemic to open virtual meetings, and we went to virtual global meetings last year and just this year. MCBK has a vision that was developed and expressed as a manifesto, a consensus document developed at the 2018 meeting, and you can see here in red the key principles underlying the MCBK vision that are elaborated in the full manifesto, which you can find on the MCBK website. The 2022 global meeting did attract participation from around the world. You'll see by the size of the dots that, well, they're not dots, the circles and dots, that the majority of the participants came from the US, a very large participation in England, and that reminds me of something I didn't mention or emphasize enough that the UK in 2019 picked up the MCBK theme and started its own chapter, beginning with the seminal meeting in 2019, but continuing to this day. And the US and UK axis was really instrumental in helping us conceive of MCBK as a global movement. And here you see the extent to which at last year's global meeting, we had significant global representation, and where chapters are either in formation or where there's interest. At the MedInfo event in Sydney this July, we were fortunate to have an MCBK harbor cruise and several panels and workshops. And then we just finished the MCBK 2023 global meeting. We also are employing the Learning Health Systems Journal, which I'm very pleased to be the editor of, which has been publishing now for 7 years and has the first impact factor that is very respectable for a first impact factor, and 110,000 article downloads in 2022 as the official journal of MCBK. And we are making the relationship between the journal and MCBK even stronger by publishing knowledge objects in the journal, peer-reviewed as a special type of publication that we hope will be more prominent. And it turns out just today, our special Computable Biomedical Knowledge issue, edited by Gunesh Koru of the University of Arkansas, actually, it appeared today. I didn't have a chance to change this slide, but that article is now live, and that issue is now live. It contains many examples of computable biomedical knowledge on the website of the journal. So the North American chapter, now that it's a global organization, MCBK North America is now live. We are going to establish it. We are in the process of establishing it as a membership organization open to everyone. And we very much hope this will be a joint US and Canadian enterprise. We have 198 charter members already. We will have a meeting of MCBK North America this coming February. If everything about MCBK is available at that website. And if you would like to join MCBK North America, just send an email to this address. So this brings my presentation to a close. I hope we do have some time for questions. I will stop sharing my screen, and we'll very much appreciate hearing the comments and questions that you have.